dive in a second. And okay, so welcome back everyone for the third and final lecture in Asaf's course on local and global structure of uniform spanning trees. And Asaf.
All right, thanks, Omer, and thank you all for coming back, and for those of you who are listening to it later. So the plan for today is to finish briefly the proof that I started showing you last time. I'll remind us all what we did and how it implies the proof. But first, I promised Rick to answer his question. So Rick asked. He's not necessarily here because I already updated him in an email just to.
I'm here.
Oh, hey, okay. So you'll have to listen to that again. Sorry about that. Rick's question was if you have a sequence, GN is a sequence of finite graphs with high girth. With girth tending to infinity, and let's say the degree is fixed. Degree is 3. And, it doesn't really matter in this if the graph is regular or not. So does the UST of the GN converges? Right. If so, to what? And this is actually not very difficult to answer, even though I didn't have an answer on the spot. And the answer is in fact more general. This was your question, Rick, right? Yeah. So the answer, I mean, or in other words, you can ask this: is the local structure of is the local behavior of the uniform spanning tree locally behaved? Okay, they're two local in that sentence. One is the local structure, meaning you choose a random vertex, look at the tree, right? And can this distribution change if I change the graph in a very far away in a far away part of the tree? And the answer is that it is not. It cannot change. So the answer is even more general. If GN converges locally, so perhaps there are some things in this that I haven't defined. Right? What is this locally? To some random, GN can be fixed, but they still converge to a random a unimodular graph. So in the case of Rick's question, this will just be the 3 regular tree, right? If GN converges locally, then the UST of GN, viewed as a finite random graph, converges locally to the wired uniform spanning forest, whatever that is, of G, right? Of the infinite graph, the Wusserl. So it seems. So this is just one of the possible generalization, the extensions of the uniform spanning tree to infinite graphs. And on the regular tree, it just turns out to be an explicit branching process conditioned to survive. Right, so this is a claim, right, and this is a claim, and the proof the proof is not very difficult. I will just sketch it. The UST of GN stochastically dominates the Wusserl of G on a fixed neighborhood. So if you look at the ball of radius 10, in Gn, and in G, the one in Gn will be bigger, right? But on the other hand, the average degree, so it could be coupled so that the Wusserl is contained inside the finite graph. But the degrees, right? The degree, the average degree of UST Gn, it's just a finite tree. It's 2 minus 2 over n. And the average degree of the Wusserl is always of the wired uniform spanning force on any unimodular random graph is 2, right? So it's so there's a coupling between the two measures, right? One is the limit of these things, and the other is the Wusserl of G. One is contained in the other, but they have the same expected degree, so they have to be equal, right? So this answers your question. And in our setup, where our finite graphs are infinite, this is a useless theorem because they will never converge locally. But the difficult question, right? It makes it sound as if on finite graphs the difficult question is or the question is meaningless. But of course, on a tree it's very easy to describe this object, right? But on other graphs, on Z2, then your work with David shows that there are many, that it's actually quite hard to describe this this object, and there are many interesting things going around there, right? So, so I think that answers your question satisfactory. Okay, great.
Thanks.
So I was about to show you the theorem, right? Just reminding you, theorem together with Yuval. Right, Gn finite, connected, regular, degree tending to infinity, and UST of Gn converges to the Poisson one branching process conditioned to survive. And let me show you the proof. What we showed, we developed a theorem. We proved the theorem, which I will use today. So this was last time. Right, I start, this is a k-step random walk with one k-step random walk. K is fixed, x0 is uniform. Right, then the resistance between x1 and the set x2 up to xk is of order k divided by k minus 1 times d plus lower order terms with high probability. And this is what I showed to you, and what was left to determine or to see is how does this theorem this one gives the theorem that I claim. What does this even have to do with USTs? We remember Kirchhoff's theorem, which is the start of all of this, right? The probability that an edge is in the UST is the effective resistance across the edge. So let me now sketch you the proof of the main theorem. Proof of main theorem. So this will not be a full proof like I showed to you all the way up to now, but I will indicate what are the easy parts, or I will indicate where I'm doing small jumps, and but there's one thing that I will not show to you, and that is a tightness statement. So let me just state it, but I will not prove it. I was surprised when we worked on this. This was something that we thought would be completely trivial, but it is actually not, and there's a good reason that it is not. So when you do these limiting procedures, you have a finite finite graphs. You take USTs, or when you have any kind of a measure on finite objects converging to some infinite, there's always the possibility that some mass escapes to infinity, and in some cases you want to rule it out. And this is the statement. The limit as m tends, so this is for any fixed radius. the limit of the of the probability that the ball in Tn, right? Tn is always going to be the UST of the nth finite graph, that the ball around the random vertex, x is a uniform vertex, the probability that this is bigger than m goes to 0 uniformly, and n. Right? So if I choose a large m, this will be small for all n's together, and it seems natural that you would need such a thing. It is surprisingly not trivial to prove, and perhaps it's trivial for r equals 1. Trivial for r equals 1, because r equals 1, then this random variable, it's, yes, right.
Can you read the statement again? There was a lot of symbols, and I'm not sure I understood the correct.
So I'm taking the limit as capital M tends to infinity, the supremum over n.
M, okay.
Yes, yes, sorry about that. This is m. Yes. I try to use as little Greek letters as possible.
Okay.
Yes.
Go ahead, keep reading though. Sorry.
Okay, please stop me if I'm unclear.
Yeah, so this just says that the size of the balls are tight.
Yeah, just that the sizes of the ball seen from random points are tight, and it's trivial for r equals 1 because this is just the degree, right? B T N X R is just the average degree. Average degree, right? And which is, of course, its expectation is finite. It is 2, right? So of course, for all n, right? So of course, you apply Markov's inequality, but already for r equals 3, this expectation can be unbounded. This can be unbounded. So that means that for general R, the bounds that we get here, we get some explicit bounds in M, are extremely bad, right? And they are really can be bad because you do have examples where this could be this random variable could be very large, but could be extremely large with small probability. You can construct an example, right? For instance, something like this is a D. You start with a deregular tree with 2 levels, and then you attach cliques. Each of them have D vertices, such a way that everything remains regular. And you can see that you have some small probability of X being here, right? And in that case, the size of the family or the size of its tree that it sees after 2 steps can actually be quite large. So for r equals 3, this could be unbounded. We actually do not know the answer for r equals 2. It's just a curiosity. We do get that the probability that the ball of radius 2 is bigger or equal to m is no more than 1 over m squared. So it's almost the second moment is finite, but not quite. But let me not. This is just a digression, right? So this is a statement that I will not prove. We'll just skip the proof.
Are there finite lower moments, like 1/10 moment or something?
You mean that it cannot be very small?
Well, you said the expectation might be infinite, but maybe like the expectation of the square root is finite or something.
But if the expectation is finite, I mean, it's an integer random variable. If the expectation, then the expectation of the square root is also finite. Perhaps I didn't understand your question.
But
Yeah,
not
I'm asking
conversely.
Sorry?
So this is a way to get the tightness if you show that for some epsilon the expectation of the ball to power epsilon is finite.
of a general R. Yeah. So we do get bounds that we get explicit bounds on this probability, which tells you that some very small moments are finite. right? But we do not know a priori how to prove that the very small moments are finite. Yes. Okay, so you could take it's not a very long proof, but it's cute. It's not trivial. Okay, but let me try to convince you. Given this, how do we prove the main theorem now that we know this? So now that we know this, it's pretty straightforward, right? So we need to find the limiting process. So for instance, we want to find the density or the probability. Let's use the probability of seeing a ball of radius 4 or 3, sorry, that looks like this, right? For instance, but let's do this particular example, even for the proof of this particular example, we'll have to first show something for all possible examples, right? So this is a ball of radius 3. So what we're looking for is just the probability that it looks like this, and all the edges emanating from it, all the other edges emanating from each vertex are closed. So here I have a bunch of closed edges, right? For the last vertex, I don't know if the edges emanating from it, other edges emanating from it are closed, right? So this is just going to be, right? This is the probability that we see this in the UST, right? So for this, I could just sum over all the possible choices of a path of length 4, right? And ask what is the probability that, right, this path V1, V2, V3, V4 is in the UST, right, Tn, and all other edges are closed. So it's an intersection of 2 events. So the reason that I did all this fuss with the random walk, right, because it's simply because when you see a sum over paths of length 4, your natural instinct is just to change this summation into a random walk question, right? So what we showed is that with high probability, for most occurrences of V1, for most paths of V1 which are named V1, V2, V3, V4 in the graph, most of them satisfy this kind of inequality, so that the resistance from the first vertex or from the last vertex to the first 3 has to satisfy this. So this is what we've discovered. So let's use this information. So I'm skipping a little bit, and now I'm on the obvious step of take all the paths that do not satisfy this condition, right? Right, and throw them out and somehow bound this probability that is written there by something small enough. There's a small amount of them, so I can assume that all the paths in the graph of length 4 have this property of the effective resistance, right? And so I'll first compute the probability that the path is open, right? So what is the probability that it is open, right? So what is the resistance on, or let's just say first, how many paths are there, right? So there are n d cubed. This is the number of V1, V2, V3, V4, right? The number of such possible choices. What is now the probability that the first edge is open, right? It's just 2 over d, right? That's what we proved. This is the, right, with high probability, the first edge will have 2 over d resistance across it. Right, so we've opened the first path, V1, V2, and now we condition on it being opened, and now we ask, what is the probability that the edge between V3 and V2 is open in the UST? But once we conditioned on V1, V2 being in the UST, we contract it, and now it's a vertex of degree 2D, right? And V3 is of degree D. Right? And what we know, this doesn't really matter. What we know is that this is, now we can apply this theorem with k equals 3, right? We have 3 vertices, and we're looking for the effective resistance between V3, which will be x1, and V1, V2. Right, so it's k equals 3. I get here 3 over 2. 3 over 2 divided by d, right? And the last one is v4. I get 4 over 3 d. Right, altogether, this is, and I also, of course, there's also a 1 over n that I forgot at the very beginning, right? Because I have to have the random vertex. This 1 over n is just, oops. This 1 over n is just the probability that x equals v1, right? That the first random vertex that I chose is v1. Okay, so altogether I get here, what do I get here? And of course, now I have to have the probability that all other edges are closed. Closed, so all the factors of d disappear, and I just get 4 here. Okay, times this probability that all other edges are closed. So here is the place, and here I have up to here I have essentially inequality. Of course, I'm forgetting I'm neglecting a bunch of errors that I will. I'm neglecting a bunch of errors that I will not bother you with the bookkeeping. And now I want to, so here is where I use the theorems from before, and I really use the fact that this V1, V2, V3, V4, I'm averaging over all the possible paths in the graph. But now I've done that, and these edges now that I have to make sure are closed, all other edges coming out of V1, right? The event here is that these approximately d cubed edges are not in the UST, and they are definitely not random, right? They are definitely, I've already done my random choice, and now I cannot use it anymore. But on the other hand, we have one side of the inequality of the resistance was deterministic. If I know, I'm reminding you the observation, the resistance between x and y is always bigger than 1 over the degree of x plus 1 over the degree of y plus 1. Right, so I can continue this inequality from here and write and the probability that an edge is closed, right, is 1 minus this effective resistance, right? So I'll write here an inequality in this side, right? And I'll copy the 4. And now let's see what I should write here, right? And what I should write next. So once I've conditioned on the path V1, V2, V3, V4 to be open, right? I contract it into a single vertex, V1, V2, V4. And now I'm looking at the possible edges coming out of this set. So I have 3D edges that I want to close, that I want to calculate to upper bound the probability that they are closed. Right, these are these edges coming out of V1, V2, V3. These are the edges here, and I also have D more edges coming out of V4. Of course, it's not exactly D, right? There could be some repetition, right? So it could be D minus 3 or D minus 2, right? There could be some another edge coming out of here, but this will not be material, right? So the pink edges, I leave them alone. I require nothing of them. So what is the upper bound on the probability that these 3D edges are closed? So let's just do it, right? So at each time, so I begin with so let me just right. I write this product from I to 3D, and once I've closed I vertices, right? So the amount of, so once I've conditioned on I of these edges, sorry, not vertices, being closed, right? I have here 3D minus I edges, 3D minus I edges left. So let's draw it like this. This was the vertex V1 up to V3. I've closed I edges, right? So the degree of this vertex is 4D minus I, right? This is the degree of this large vertex, black vertex, and now this vertex has degree D. right? Because degree at most d, right? Of course, there could be other edges here, but it could be degree at most d, which is exactly in the inequality that we want. So what we write here is 1 minus an upper bound, sorry, a lower bound on the effective resistance, and this will just be henceforth because of that 1 over d plus 1 over 4d minus I. Right? This is the upper bound. Let's compute this, right? And this is really an upper bound. This is not tight, at least from what we know now. This is not tight. Of course, I will try to convince you in a bit that it is tight. So this is e to the minus the sum I from 1 to 3d of 1 over d plus 1 over 4d minus I. These are always right.
Why
yes?
is it 1 over? Why do you have the 1 over d there?
Because d is an upper bound for the degree of the red vertex.
Don't you need a lower bound?
No.
Okay.
Right. If I write there, if instead of d I would write something smaller, right? That would be better, right? So
yeah. Oh, sorry. Okay.
Yeah. I made the same confusion like 5 times while thinking about this. So so I have here the 4. I have e to the minus 3 from the first term, and then I have e to the minus 2. This sum of 1 over 4d minus I. Sorry for doing this very slowly. I just want to make sure that I get the computation right. Right. So this is like summing. So this goes from 1 over 4d to 1 over 3d, right? No, from 1 over d, right? 1 over d plus 1, all the way to 1 over 4d, right? So this is just a log of 4, right? Which cancels the 4, right? So what we get in total is e to the 1 over e cubed, right? Plus little o of 1. And if you remember, this is the number that we expect to get in a Poisson 1 branching process, right? Because you need the first progeny to have 0 children. That's 1 over e. The second and the third, right? So we get that, but we only got an upper bound. So this is only an upper bound, only upper bound. But it is. We could do exactly the same thing. Instead of taking a path of length 4, right? We could take all possible graphs of on radius 4, right? We could calculate. Sorry. So we could do the same thing. We could get the right upper bound for any possible fixed graph, fixed tree of size 4, of any size, right? But all of these numbers sum up to 1, right? Because these are the numbers that you get from the Poisson branching process. They all sum up to 1. So all of these upper bounds that you get from all of the possible choices, they all sum to 1. And because of our tightness, right? That means that every time that we had, right? That means that the quantities that we're upper bounding also have to sum up to 1, right? So we have 2 sequences. One is bounded by the other. They both sum up to 1. They all sum up to 1 by tightness. We must have had we have equality, right? Plus little o of 1 everywhere. Right? And this finishes the proof. Okay, so this was the easy derivation given the lemma. This is what I wanted to say about the local structure of the UST. I hope you enjoyed it. Do you have any questions before I tell you a short story, half an hour long, about the global structure that I thought it would be longer, but I thought it would be longer. So feel free to ask, or I'll just, if not, I'll just proceed to tell you something about the global structure. This is unfortunately not as fun as what I've showed to you in the first, in the second, or in the local, in the theorem about the local structure, and that is why I'm showing it to you last, right? Even though some people save the most tasty dishes for last, I'm the complete opposite. If you have something tasty on your plate, you must eat it before everything else, because the world can end at any moment. Or even worse, you may lose your appetite. The global structure is actually the proofs are not as pleasant, but the theorem is very appealing, and I'm reminding it to you. So this is a theorem together with my new postdoc Eleanor Archer and my student Matan Shalev, and it is still a work in progress, and we hope to release it in a little bit. I'm just reminding it to you, and let me just state it in the specific case of the high dimensional torus, which in my opinion is the most interesting, but other people seem to like the hypercube more. I make no judgment on people's choices. So this is our setup. D is bigger than 5. We're looking at the 5-dimensional torus. Tn is the UST of Gn, and the claim was that if I look at the diameter of this UST, there exists some beta depending on D. If I look at the diameter of this UST, divide by square root of n, then this converges in distribution to this random variable, the diameter of the continuum random tree, which you could just describe as a certain functional of the Brownian excursion. So this fairly well understood random variable as much as we can. So I'm going to try and tell you a few words about this proof. But in fact, as I've hinted in the first lecture, the proof is gives convergence to all sorts of functionals, not just the diameter, because we proved this metric space convergence, right? So, but I don't want to bore you with the definitions of the topology that we're using, that is used, not we, but that people have been using, Gromov, Prokhorov. It's a topology on the set of metric spaces, or even on measured metric spaces, which if you prove convergence with respect to this topology, then everything you want, you get for free. The diameter, the height profile, and everything you want. So in fact, we have a metric space convergence. We prove metric space convergence. Right, so the same beta. We look at the metric on n points induced by the, I guess it's not n points, it's n to the d, I guess, the number of vertices. So I guess, yes, I made a so let's call this m, yes, and fix it so that n is the number of vertices. Okay, this some people call it v. I don't know. I grew up in Tel Aviv University, where n is always the number of vertices, and you can't go. Once you learn something in high school, you can't change. Square root of n. This converges with respect to this Gromov, Hausdorff, Prokhorov. At least the people that I see on the video, I think know this topology much better than I do. To the CRT. So in this topology, but I like keeping in mind this theorem about the diameter, because the diameter is somehow of a canonical example of why you really need this Gromov-Hausdorff topology. So this is what I'm trying to convince you in this in time of ILF. So this topology is strong enough to capture enough to prove convergence of the diameter. So let me tell you about a slightly weaker topology, right? And this is the result that we rely on in this work. So this is the, we rely on a result by Paris and Ravel from 2004 on the following. I don't know why I'm writing following this, right? So this is a theorem by Paris and Ravel, 2004, right? And this is what it says. And so under the same setup, so you look at the same setup as above, you look at the high dimensional torus. X and Y are two uniform points, independent, two uniform vertices. Right? Then the probability that the distance with this beta, the distance between two vertices then let me put it differently. The distance between two randomly chosen vertices behaves the same as it would on the continuum random tree. Right? So it turns out that on the continuum random tree, you sample two uniform vertices. The continuum random tree comes with the canonical measure, a probability measure allows you to sample points. This is lambda here. So they proved this statement, and in fact, even more. Also, if you choose k random points, x1 to xk, random vertices, the k choose two distances, pairwise distances converge to the corresponding to the CRT. Right, to the corresponding k choose two distances in the CRT. Okay, and this is a very nice result, also quite technical, and it's somehow easier to this result is easier than the result about the diameter because we know how to sample this path very well, right? We know we know that the distance between x and y is just in the UST is just the length of the loop erased walk between x and y. So this is a fact due to Robin Pimentel or David Wilson, depending on your history books. That the path between 2 points in the 2 fixed points in the UST is distributed as the loop erased random walk between them. So to understand this thing, you just need to essentially understand the loop erased random walk between 2 points on the high dimensional torus, which is already knowing it with this precision is already significant. And their work uses a coupling. So there's a way, because this is where the high dimension comes in. The typical size of the typical length of the loop erased random walk is square root of n, and it is much higher than the mixing time of the random walk on this graph. So in some sense, you have regeneration points. You very quickly find yourself in completely new areas of your graph. And what they do is they really couple this walk with a walk on the complete graph, where everything is much easier. So it really is a coupling result. And on the complete graph, it's not easy. Sorry, it's not hard to show that this thing holds. So there really is a coupling, and this is somehow very not a fruitful strategy to study the diameter, because we don't know how to sample the largest path in the uniform spanning tree. Right, the minute I sample it, I reveal information about other parts. So I cannot say what the diameter is. So let me just remark, right? So this, and also formally, this kind of result tells you nothing about the diameter. So this says nothing about the diameter, indeed, because you can add, for instance, add the path of length n to the 2/3 to gn, right? Because right, so if I have a graph, or if I take the torus where this holds, I take this graph and add just the straight line of this length, right, then clearly the statement will still hold, right? This statement will still hold, because if I choose two uniform points, it will definitely not have anything to do with this path, this tail that I've inserted, right? But the diameter, of course, looks at the maximal path, and this entire path will be in the UST, because then the diameter will be of order n to the 2/3. So you may ask, if you remember the first lecture, I told you that together with Peleg Michaeli, who is now it's my former student, and he's going to do his postdoc at Carnegie Mellon, and he's very nice and very smart, asks a lot of great questions. So if you ever, by any chance, go to Pittsburgh and you want to meet a uniform spanning tree, then I'm sure that he would love getting an email from you. So what we proved in an earlier paper is that the diameter of the UST divided by square root of n is a tight sequence. Also the inverse, it's less interestingly the inverse, right? So you may ask, okay, but so perhaps if you take Paris and Revel together with this result, then we're used to thinking, oh, there's this should be a compactification, a compact state. Something is compact. This is finite dimensional measures, finite dimensional distributions converge. Then this should just imply that this is what we thought originally, but of course it's not. It does not hold. So this also says nothing about the distribution of the diameter, the limiting distribution of the diameter, because you could just add the path of length 100 or 1000 times square root of n to gn. Right, so in this case, now I start with a graph like the 5-dimensional torus. I added a path of length 1000n. So this theorem definitely, the first one by Paris and Revel, definitely still holds. Our theorem definitely still holds as well, because it's still tight, right? Whatever the distribution, I mean, it's whatever the distribution was, but it's always bigger than 1000, right? So you scale it up a little bit, but it's still tight. So there's no way that this could these two results could lead to finding out the distribution of the diameter, right? But it seems very close, right? We have an object that converges in the finite dimensional sense, and perhaps you're worried about me cheating about, oh, you added something very. You made the graph non-transitive, and you did that. I can do all this cheating in a way that will appease you for any complaint that you have. I'm a people pleaser, but I could do it in any way that you can, because there really is something missing, right? So there really is what? So the question that you may ask yourself, what do you need to get GHP convergence? What do you need? What do you need to get GHP convergence? This is what we asked ourselves, and it's very nice to have friends like Christina that immediately had the right paper in their mind and told us about this beautiful work by Atheria, Lohr or Lehr, I'm not sure how to pronounce it, in the Anita Winter from 2016, right? That tells you, I will not, again, I don't want to define to you what is Gromov-Prohorov and what exactly do they do in this paper, but if you want to understand all this, this is the paper to look at, and some of Anita's previous work. And what we learned is that the missing ingredient, or what we need to get from from a statement of Paris and Revel to a statement about the metric convergence of the UST is the following lower mass bound. So it's called. So of course, it's a much more. What I'm telling you is just I'm recasting their general theorem to my specific, very small setting, and this is what we need to prove for any constant c. there exists some function of epsilon tending to 0, as epsilon tending to 0, such that for any n, any graph, the probability that there exists a vertex in this graph such that the ball around it of radius c times square root of n, the probability that this is smaller than epsilon n is small, uniformly in n with epsilon. So let's just take a look at this line. So if you take a look at this, so what this means is that if you look at any vertex, right? Well, let's state this what you need to prove in the positive way instead of the negative way. If you look at any vertex in your tree and you look at a ball of radius c times square root of n, so let's just say square root of n, you do not see too little vertex. You do not see epsilon fraction of the vertices. So this, for instance, if you know how to prove this, this kills all of these tails that I wanted to put, all the tails that I wanted to prove, all the tails that I put on my graphs in order to screw up the diameter. And notice that this statement, note that this is actually stronger. This implies tightness of the diameter, right? Because if you have such a, if the complement to this event holds, you cannot have a path that is too long, right? Because if you had a path on the tree that is too long, you have to have some place on the path where if you look at only square root n, if the path is 1,000 of length 1,000 times square root of n, then there's going to be some point on this path that if you look only to radius square root n, you see very little vertices, right? There's a function of this 1,000. So this is in fact a stronger statement than the statement we have proved, and it's reasonable because as I showed to you, the tightness is not enough to show this, and this is the statement that we struggle to prove, and it is difficult for two reasons. So let me tell you why it is difficult. So difficult for two reasons. One is that this is a reason that is very familiar to any probabilist. We need to show, right, that a certain random variable, right? Okay, let me say it in the opposite order. The first reason that it's difficult is that we need to show something that holds for any vertex in the graph, right? So if you look at the complement event, right? So need a uniformity not in n, which I care less, but in x. So this is actually quite troubling because I can do many things, you know, for a particular x. I could start growing or do exploration, look at run Wilson's algorithm rooted at that x, do all sorts of UST tricks, but eventually I will need to say something for all x's, right? So, and this is one difficulty, and the other difficulty is that even if we're looking at a particular vertex, a particular x, we have a bound of the form, we have a bound of the form, some random variable is smaller than epsilon is also smaller than that. This is what we want is also small. And this is always the difficult bound in probability because moments do not determine this bound, right? So there's no first and second moment that can do this. You need to do, what you have showing that the probability that a random variable is small in itself is the difficult part of probability theory because moments do not suffice, and you have to somehow struggle to find independence or whatever you can have by hand. So these are the two difficulties in this estimate, and let me tell you. Let me not tell you how to resolve the first difficulty. I wish you could just do that in a paper. I will skip the proof of this part. And let me tell you a little bit about how we just prove something like this for a given vertex and not for all vertices. So the statement that I want to convince you or to hint some, it will not be convincing. Let me be frank to you in the beginning, is that if you look at a particular vertex and you look at distance square root of n, there's a small probability that you will see two little vertices. And this is when I first realized this, I was surprised that it is difficult, because this kind of estimate. So I want to prove, right, something of this form, btnx. Let's just choose c equals 1. Smaller than epsilon, and that this is small. This is what we want to prove. And when I first saw this, I was annoyed that this is not immediate, because in critical percolation, which is a model that I consider, or many consider, more harder than the uniform spanning tree. This is a much easier estimate to do, right? Because you have this independence. So in critical percolation, say on a tree or on a high dimensional graph, or even a branching process, in critical percolation, this is easy. Percolation, it is easy. Easy because if the event holds, right? So if let's call this event A holds, right? That means that you will have there will be some level in this ball. So means that there will exist some I between square root n over 3 and 2 square root n over 3, where the number of vertices that you see is small. Where, let's say, the boundary of this ball xi is smaller than 3 times epsilon square root of n. Right? Because of all these levels, there like there's 1/3 times n levels there. If they're all bigger than this number, then I've already accumulated more than epsilon n. So that means I can, in critical percolation, like it's very natural to explore in a breadth first search, right? In a breadth first, it's very natural to explore, right? Because I just explore all the levels until I reach this this level I. So I've explored here. There's a tree that I've discovered, and a bunch of closed edges that I've left out. And in percolation, closed edges can only harm you. This is one of the nice things. They can only make you can only make your life worse when you look at monotone events, which is our case. So if at this area, at this level, you've only seen 3 epsilon square root of n vertices, and one of them has to reach height at least square root of n, that costs you another factor of 1 over square root of n. The probability of a critical branching process surviving for k steps is of order 1 over k. Right, so you multiply this number with this number, and you already get that this probability is small. Right, so so negative information in critical percolation works, I guess, in your favor, and in the opposite favor of the volume. Right, so it makes the volume smaller. But in the UST, this is not the case. Right, in UST, exposing closed edges. So this is what I mean by negative information. Okay, it's closed edges can, and very often does, make your expected size, expected volume large. Right, so up to this sentence is still, of course, true, even if this was a UST, right? There, if the event A holds in the UST, of course, there will be a level somewhere in between that you see very little vertices. No one can argue about that. It's just the triangle inequality, I guess. But it could definitely happen that you've discovered all this level, you've reached this thin level, and you've exposed so many closed edges. Right? So here they are. All of these are closed, so that now this particular vertex, right? There's perhaps a very long path emanating from it, and all other edges coming out of this path are closed, right? Because they all connect to the bottom. And you can see something like this, and if you see something like this, then this vertex the vertex in this vertex here has probability 1 of, you know, all of the edges of this path has to be open, right? Because they cannot disconnect the graph, right? It's a UST, so you have exposed a bunch of closed edges that make me lose this probability of 1 over n. And this could actually, you know, and of course you can imagine this can actually happen. So our goal is to prove that somehow these kind of, you don't see these kind of pictures, but as you can imagine yourself, just quantifying what is it that you want to see is difficult. So of course you need to go through some indirect way, and this is where at least from this perspective, what comes to our what comes to our rescue is the negative correlation property of the UST, which is weird that will come to our rescue, right? Because we want to show that the probability the volume is small is already small. It doesn't quite fit the notion of that, at least I think of as negative correlation. If a part of the tree is large, at least then some other part will tend to be small. Okay, so it doesn't quite fit what we want to do. But so here's a very high level sketch of how to do this. So you don't explore according this way that I did here. You do not explore in a breadth first search. This operation is very unnatural to the UST, and I would actually love to find a way to do this. There's all sorts of sampling algorithms, Aldous Broder or Wilson. There's the interlacement Aldous Broder by Hutchcroft. There's all sorts of methods. And I would love to find some algorithm that samples part of this, not all of it, because that I know cannot be done, but part of this this graph distance ball in the tree. It's not immediately clear that it's possible at all. So what we do instead is that we take this vertex x and we sample a long path, for instance, to some uniform vertex v. So this we could do in a way that doesn't have, so this we just use Wilson algorithm, we sample a large path, which we use as our backbone, and now we study the parts of the tree hanging on this path. And so we split it into several intervals, and we look at the parts of the trees hanging on this path. And we call their, you know, when we look at their volumes, their volume is xi. So let's say if this is the ith interval, then xi is just the volume of trees hanging on it. And what is classical is that these xi's, or not classical, but not very hard to see, is that xi are negatively correlated. And it's somehow surprising that once you think about it a little bit, if two things are negatively correlated, then also their inverses or their complements are also negatively correlated. So in fact, it turns out this is slightly harder to prove that these things, these random variables, are also negatively correlated. So you can prove this. This requires some. This is definitely not a classical UST thing. And once you play along with this, you can actually show stronger negative correlation, stronger negative association. I keep confusing these words, which kind of shows that I don't really know what they mean. But you could prove something. You could prove something like this, which right. This is, and this is the kind of inequality that you very much want to prove, because it allows you to show that this sum over the xi's is concentrated around its mean in this usual Zuma hefting inequality. So you have exponential concentration for the stuff hanging on the main branch. But what is its expectation, right? This is pesky, right? Because if we condition, if we have this path, how do we say what is the expectation of all this mess, of all these xi's? And this is where, if we would have been working on the complete graph, things would have been better, because on the complete graph, all simple paths of the same length are equal, right? In the eyes of the one above. But here, of course, on the torus, it is not the case. So we really do have to work in order to show that this path that I've sampled on the first round is very well behaved, because we have to rule out that this path looks something like this, right? Or somehow loops around itself around the torus. So this is actually stuff that people have been doing, Greg Lawler and others, that in a high dimensional setup, the loop erase random walk looks like convergent. So we know this is a statement by Lawler. It converges to Brownian motion. So, and we need a whole bunch of slightly stronger estimates to show that it looks good. Every sub-interval looks good. And once you know that every interval looks good, and I haven't defined to you what good even means, then it tells you that the expectation of the trees hanging on it is what it should be, right? So we plug in this together with this negative correlation, and with quite a lot of work, it gives us what we want. And I haven't told you at all how to make this estimate uniform over all vertices, and this is something that is completely new. We haven't seen it anywhere else, but it's just one estimate. So unfortunately, when you put all of these together, it turns out it's not 100 pages, but it's more like 40 pages, and it could be not fun to read. But we will make sure that at least the introduction is fun to read for any of you who wants to enjoy a nice bedtime reading. So thank you for your attention throughout this course. Omer, I'm finished.
Yes, so we can all unmute.
Thank you.
Asaf for the very nice course.
Thank you.
And we can have questions.
Yeah, maybe I had a question. So you were talking about in the local limit D going to infinity.